Hi everyone. Thank you for coming on a Wednesday evening. I'm excited to be here. I'm a first year PhD student at MIT. I work on multimodal AI and human computer interaction. I'm co-advised by Professor Paul Liang at the Multisensory Intelligence Group and Professor Patty Mays from Fluid Interfaces Group. So today's talk is going to focus on something that we want to improve the model capabilities, but we also want to examine how it affects us as human. So I'm calling this talk as Beyond the Black Box, Vision Language Models that Explain and Empower. So the overview of this talk, as I mentioned, it would focus on vision language models that explain. In the first part of the talk, I would focus on a work that I collaborated with Adobe Research, wherein we went deeper into the attribution sides of PDF. What I mean from that is what I'll explain in the next slide. And the second thing is vision language models that empower. So a lot of us come across AI-generated content and misinformation. So we'll talk about how can vision language models or AI agents could help us improve as human so that we are able to learn and detect them. So let's get into the first part of the talk, that is vision language models that explain. If you look at this image, in 2024, Adobe came up with this feature that was added to Adobe Acrobat, and it's called AI Assistant. It's very common now when we chat with ChatGPT, Claude, and all sorts of AI agents, right? We can ask questions, it gives us the answer, and it references from where the answer has been collected. So this is pretty common when we are dealing with PDFs. But PDFs are not just text, it's complex. It has charts, it has tables, and it needs a lot of analysis to get answers when we are analyzing charts and so on. So real-world documents are complex. It contains performance report, different type of charts, pie charts, line charts, bar chart. It could also have tables, as I mentioned. So in this project, we went from attributing text to attributing charts. That is, how do we attribute charts? How do we reference charts? If we are asking a vision language model question from the PDF that needs a lot of analysis, mathematical reasoning, how do we attribute it to the chart, or how could we define fine-grained attributions? So what does it mean to attribute charts? Let's look at this image. We have a graph over here, which is population of Massachusetts across several years, from 1990 to 2020. This is a very simple chart. We ask vision language model a question, it will probably give us an answer. However, we are not sure if that is correct or not. So how we are defining attribution to charts is we are defining it as creation of bounding boxes on the chart so that when we are asking question, it gives us an answer, and it also directs us from where the answer is being extracted. So in our project, we defined attribution for two types, which is attribution focusing on visual question answering. That is, given a chart, if there is a question answer pair and we get the answer from the VLM, how do we get from where these answer has been extracted? It takes a lot of time as humans to go back to the chart, understand what mathematical calculations happening, and it kills time. So to solve that challenge, we proposed attribution based on visual question answering. If you look at this image, the question is how many values are below 40 in unfavorable condition. So unfavorable is represented by the orange line. If we want values below 40, we'll start counting like this. And vision language model can give us the answer. So what we proposed was, apart from giving answer, it also needs to give us bounding boxes so that we could easily interpret from where are those answers being extracted. Similarly, we added visual question reasoning, not just based on question answer, but we wanted to go a step further and attribute based on reasoning. So same, given a question and answer pair, there's also a reasoning. Now reasoning are multi-steps. Reasoning cannot be in one sentence. So we go from, let's say we want to draw a bounding box on this chart, and the first reasoning that comes out if we give this chart and question to a vision language model is the orange line represents unfavorable. So the model needs to understand that it only needs to look at the orange line that is representing the unfavorable condition, so that it could interpret then, okay, what is the value of unfavorable in the year 2015, which is 54. So the first bounding box that the model we trained created was unfavorable, a bounding box on it, which we are calling as attributing charts based on visual question reasoning. To assess the performance of existing models, we did a small POC to understand how GPT-4o, GPT-4v, and Claude 3.5 Sonnet was performing, not on attribution, but whether given a chart and question, seeing if the answer is correct or if the reasoning is correct. And we found out that the models were not doing really great back then. This project is something that we explored in 2020. It started in 2024, so the results are back from a year. This could have improved a lot by now. So chart plus question passed through vision language models and then annotated by humans. We got these results, and we then went ahead and had Claude 3.5 Sonnet as our baseline. Now, what are the challenges when we are dealing with attribution of charts? The first thing is there's no paired data. That is, if chart and questions are there, which is easy as human to create, but there's no correct reasoning with that. Sure, we can pass it through vision language models, correct reasoning could be collected, but we do not know how correct are those reasoning. There's no paired data on chart for questions, on chart and question for fine-grained attribution, that is no bounding box related to those answers. And there's no automatic evaluation that has been defined for fine-grained attribution. So these are the three things that we focused on. So we needed paired data to solve this. We went ahead and hired annotators to do that. The attribution annotation task went in 3 stages. First was reasoning, validation, and correction, which was given a chart and question. The model gives us reasoning steps. We then passed it through a bunch of human annotators to annotate step-by-step reasoning by saying, okay, this reasoning is correct or it's not correct. If it's not correct, they rewrote the reasoning step, and then they drew bounding boxes, which went ahead, which helped us with the data collection on ground truth pairs for attributing charts based on answers. And then we collected data for reasoning attribution, that is given step-by-step reasoning. We linked it with chart, and it connected us to bounding boxes. So we have some kappa score. Kappa score is inter-annotator agreement between 2 annotators. That is how usually 2 annotators are agreeing with each other. We did it on line and bar chart, 1000 line and bar chart. So we had good kappa score. But when you see stage 2, which is answer attribution, that is, as humans, how would somebody draw a bounding box representing an answer, would vary a lot from what other person would think when it comes to chart question answering. So we had pretty decent IOU score, which is intersection over union score, that is collected to measure the human annotator agreement in those scores. So the data set that we created was 500 line and bar charts paired with question answer pairs. It has now reasoning steps, attributed question answering, and then reasonings were attributed as well. We went ahead and tried zero-shot prompting for attribution as a first step to see how the models were performing. So what zero-shot prompting mean is you give it a prompt, you're a helpful assistant, and respond and mark down, help me with my math question. So the chart chart image goes, the question and answer text goes, and we are asking it to output a list of tuples, each containing coordinates x1, y1, x2, y2, representing the bounding box that would tell us how we are attributing charts based on vision, question, answering. Similarly, we went ahead and we tried few shot prompting. So models were not doing great when we tried it, and we incorporated reasoning steps into these, and we found out that with reasoning steps, it kind of improves. So we introduced radar, reasoning guided attribution framework, which is given a chart and question answer pair. We are passing it through OpenAI VIT large model that gives us the chart tokens. So the chart is getting converted into tokens, and the question answer pair is passed through a language model. It gives us language tokens. Combining both of them, we are running a partial LoRa, which means we are only trying to pass the tokens, the vision tokens, so that the training time is reduced and we generate reasoning out of it. So we get the reasoning out of it, we repeated the process, and then you combining reasoning, question answer, and the chart, we generated attribution. So this paper is accepted at EACL, and that's how we got the generated attribution out of it. Now, we evaluated the reasoning quality that we generated using radar, which was, so both chart types show consistent performance with BERT scores and semantic textual similarity around 75% and 89%, showing strong alignment between machine generated and human reasoning. So radar showed a really high alignment for reasoning quality evaluation. The main finding of this work was incorporating step-by-step reasoning step led to improved attribution. These are some of the results that we had. We pass it through GPT-4o zero shot. So this VQA means visual question answering. Given a chart and question and answer pair, we are attributing line and bar chart. If you look at these numbers, they are pretty low. So it is a very difficult task to solve for vision language model because it involves so many step-by-step analysis, reasoning, and being correct at all of them to then predict the bounding box. So radar automated reasoning means we are directly generating the reasoning. We also have radar human reasoning, in which we are not relying on the model, but we are incorporating human annotator reasoning to see how well the model does with the attribution task. Our results suggested that we had gains from like 1% to 19.7% with human reasoning in case of bar charts. When we are incorporating reasoning step, it led to improved attribution in bar chart and line charts. It reduced a bit when we removed the human component and had machine generate the reasoning. So that's the result we had from incorporating reasoning steps that led to improved attribution. And not just line chart and bar chart, we went ahead and tried how would it do if it comes to pie charts, because we wanted to generalize and scale the system. So we extracted 1068 pie charts with their question answer pair from chart question answering dataset and processed them through the 3 steps that I mentioned before, which was reasoning generation, attribution generation, and answer generation using feature attribution. So what is happening over here is, given a pie chart and a question, what's the percentage of people using latents? So given a question and a chart, the reasoning generation model, which I explained in the previous slide, it generated the reasoning. The reasoning along with the chart and question is then passed through attribution generation model, and it then gives us a bounding box on the chart, which we are seeing as chart attribution. Now using this selected feature, the selected region of the chart, we then pass it through a feature attribution model, which means that we are just passing that region of the chart that comes inside the bounding box, and we are trying to predict how close it is with the ground truth. Is it exactly same, or there's some discrepancies over there? So we were able to generalize and scale the system, and we found out that the generated answer achieved a word score of 0.9. So it means that the framework, which is very simple as incorporating reasoning steps in an open source model, helps us improve attribution capability of charts. So this is what is also running in the backend of Adobe's Acrobat right now for chart attribution. All right, so this brings us to the part 2 of the presentation, which is vision language models that empowers human. So I want a raise of hands from people in this room who feel this is a real image. All right. Okay. So in May 2023, this image went viral, and it was an AI-generated image of Pentagon. It caused dip in stock market price. A lot of people thought it was real. A lot of retweets went on. So it's important as we develop model capabilities, we as human need to also improve ourselves to distinguish between what's real and what's fake. So we ran a month-long longitudinal study to do dialogues with AI chatbots actually build lasting misinformation detection skills, or do they create dependency that undermines humans' independent judgment skills? So we developed a system. We also ran a month-long longitudinal study, and we have some conversation analysis. So for the system design, we use React-based front-end user. News headline image pair is what the person who is interviewing would look at. And there are some dialogue generation through GPT-4o. Through Google search, it looks into the news and whether it has been reshared or debunked. And then persuasive dialogues are being generated so that it teaches humans what's real or what's fake. So yeah, that's what the interaction flow looks like. A user comes to the system, they rate whether that news is real or fake, give it a confidence rating. Dialogues are being generated, 9 rounds of conversations, and then they re-rate the dialogue again. So we use this data set that contained real and fake images with headline pairs. And the study design was, we recruited around 105 people. Out of them, only 67 completed 3 phases of the study. How human studies are conducted is people are recruited, they provide consent, they fill demographic survey, and then they rate, seeing a bunch of news items, whether they feel that's real or fake. They then interact with the persuasive AI and then rate the news item again. And we collect rating on their learning before and after, and they fill some of the experiment survey. This went for like 3 phases in a month, and we collected 7,203 human AI conversation pairs and 45,036 participants' judgment on news authenticity. So learning effects of current AI system, which is the main finding of this paper, that is, with AI support, significant increase in discernment accuracy is what we saw. Once you are interacting with the AI, you might feel that you are learning and your judgment would change. But when we did the month-long study, we saw that people's ability to discern between what's real and fake after a month decreased by 15.3%. And using the conversation, we found out that using guided questions was strongly correlated with learning, and asking about their confidence or just stating the facts were least associated with learning. We also did a bunch of human AI behavior analysis, which I feel is pretty interesting. So conversational behavioral patterns showing increasing human agreement with AI, that is, is it that when we are interacting with an AI system, is it that we as human agree more or AI agrees more with us? So we found out that it has been increasing throughout in the month-long study as humans from 23% to 28.5%, while the AI agreeing with humans was pretty less. And independent thinking capabilities of people were low throughout, as well as we observed declining probing behavior, or humans were not asking enough questions. So those were some of the human AI behavior analysis. And coming back to the main finding, which is AI assistants improved immediate performance while it declined after a month. So this paper would be presented at the conference on human factors and computing system next month. So that brings me to the end of the talk. We spoke about longitudinal study, chart attribution, and if you want to discuss more, feel free to reach out. I'm open to questions.